webinar is organized by different organizations. So the initiative comes from the AFRAN. It's also led by HTO Lyon. So thank you for organizing and organizing the translation as well. The Gisi HED, the Embassy of French in Australia, the Australian Embassy in France, via the Australia Now program, the association called GREY, and the O2 Research Foundation. All of these partners have joined together to organize this first webinar. Perhaps there will be others to follow. The ambition is to share knowledge with researchers, with practitioners, and also to foster international collaboration. So the webinar is made up of fairly short presentations, and they will be followed by 1 or 2 questions so that we stick to the timing. And if ever you need further details, then the speakers normally should be leaving their email address in the chat, so you'll be able to contact them. So this is the program for the webinar. So the opening will be given by Professor Katherine Daniell. Then there will be a first part where we focus on innovative examples of metrology, and then we'll be focusing on drones or unmanned aerial vehicles. And then we'll be closing with Dr. Nathalie Simonel and Namour, who will be talking to us about financing tools available for French-Australian collaboration. So the idea is really to share knowledge and to start collaborative work. So we're going to start straight away with Professor Katherine Daniell, who's going to be talking to us about metrology. She'll be going back over different changes and revolutions in this field.
Bonjour à tous et à
Yes, hello
toutes.
everybody.
And good evening, everyone. Thank you, Frederic, for the introduction. And on behalf of AFRAN, the Australian-French Association for Research and Innovation, it's also my great pleasure to welcome you and to provide a few opening remarks. As part of the introduction, I thought before we get into the future and the innovations of metrology for water systems with our 2 sessions, it's maybe worth exploring a bit of the French and Australian history of the research area and a few stories of the innovation that shaped the direction of the area. Now, I'm going to frame these in terms of cybernetics, as my main role outside of AFRAN is in the newest school at the Australian National University, the School of Cybernetics, where for the purposes of this presentation, I'll take the broader French definition of cybernetics as the art of effective action and governing in complex systems in general. So effective action in governing systems is greatly supported by having access to reliable and specific information. So communities globally have worked to measure, standardize, and share information based on the same knowledge systems for millennia in order to facilitate exchange, calculation, and inform understanding for science, and also more purposefully for informing action in the world. And as a place to start these remarks, I would like to acknowledge that I'm coming to you across the airwaves and digital connections from Ngunnawal and Ngambri country, a country that's never been ceded and will always remain sacred. And I pay my respects to elders past and present. When we think of water governance and informed effective action, we can see that generations of Aboriginal people over millennia have taken cybernetic approaches, those approaches that carefully integrate technologies, societies and environments and their interactive feedbacks. And through this, Indigenous societies have been able to develop sustainable and responsible governance systems based on shared and transferable knowledge, including a range of environmental indicators. And one particularly prominent example that you can see here, and one that's of interest to me as a water engineer, is the Borona fish traps, or Bayamese Munu, which is one of the sophisticated water engineering and aquaculture structures that's been carefully maintained as a meeting and ceremonial place for different Aboriginal nations to this day. And as we continue our collective digitalisation and monitoring and modelled representations of the world, Indigenous peoples remain at the forefront of determining what roles these digital systems might play in our lives, including volumetric capture and drone technologies, and the kinds of cultural protocols that will ensure that communities can develop responsible governance of cyber country, not just sea and water country. So we could do well to see what we can continue to learn from all of these approaches. Now, for the rest of this presentation, I want to tell you 3 brief stories looking through cybernetic lenses at French, Australian, and collaborative international approaches to metrology for water systems. For my first story, I want to briefly take us back to the defining time in Western metrology and our scientific systems today, which is the French Revolution. Now, one of the outcomes of French thinking at the time and needs for governing in the new French state was the formalisation of the international system of units based on a metric system. And water was at the centre of this, where of the 3 key measures that were the metre, the gram and the litre, it was water that was the core constant, pulling these measures together, specifically that it's at its highest liquid density at about 4 degrees, 1 kilogram of water equals 1 litre. And in terms of cybernetics, André-Marie Ampère, who spent his formative years in the Revolution and was one of the founding fathers of electromagnetism and a polymath professor at the then new École Polytechnique, is considered to be the first to have coined the term cybernetique in French over a century before the term appears in English after the Second World War. And he, of course, is the namesake of the Ampère, another SI measure, and other machine builders creating cybernetic self-governing feedback mechanisms like Watt and Maxwell for steam engines are also namesakes of SI units. So we thus see a really close coupling between the evolution of metrology and the evolution of cybernetics. The next story I want to tell is an Australian cybernetic story and part of the communication revolution that was sweeping the world in the 19th century, which looks at how the connecting of different systems of weather measurement through the telegraph and a network of post offices that recorded meteorological data led to the ability to develop large-scale weather maps for Australian populations on water measures. 2 astronomers and meteorologists, Charles Todd in South Australia and H.C. Russel in New South Wales, led the charge. Now, Charles Todd developed Australia's overland telegraph line from Adelaide to Darwin in the early 1870s. And with his organisational nous, he managed to complete it and connect it to an international undersea cable, as well as to reform the postal service and turn it into an intercontinental climate monitoring network. And he was also believed to be one of the first to recognise the extent to which local climate is influenced by global phenomena like the El Niño Southern Oscillation. And as a small nod to French photographic science, he's also credited with being one of the first to take daguerreotype photos of the moon. It was actually in 1847 in Cambridge. Now, Harold Chamberlain Russel in New South Wales teamed up with Todd and a range of other meteorologists to develop standardised measurement systems based on his various self-recording barometers, thermometers, anemometers, and rain gauges, with him collecting the data through telegraphs from across the network and publishing consolidated weather maps in the Sydney Morning Herald newspaper, making this new knowledge available to the public. And the first one is on the left, and that was in 1877. And out of the Todd Adelaide, or the Adelaide Observatory, Todd produced some of the earliest continental scale isobaric weather maps in the 1800s. And in this one, observation of cloud can be seen just along the telegraph lines. You can see from north to south and east to west. And today, we may use a range of other technologies, computational capacities to develop near real-time systems at scale to develop our maps and information products to support effective action. All of these are large cybernetic systems. But if we look carefully, like the cloud that stops when the telegraph line is too far away, our systems of measurement and monitoring still have gaps or blind spots and a range of biases. So my last story is one of French, Australian and oceanic collaboration on water governance from a few years ago that was funded and supported by multiple partners, including the Fonds Pacifique, the Institut Français, IRC, IRD, Ørsted, which is now INRE, and Majula Inc. In the Kimberley, as well as the governments of Tonga and Kiribati. And the project, amongst other initiatives, uncovered a blind spot in metrology. And I want to take you on a trip out to the Pacific island of Kiribati and introduce you to 2 important objects, the bucket and the jug. So in Tarawa, the capital of Kiribati, water use data comes from the Public Utilities Board, which stated at that time that people use about 15 litres per person per day. Now, noting that the typical minimum suggested by the UN is about 50 litres per person per day, this seemed pretty low. And so one of the only ways to determine what could have been missing was for my colleagues to head out there and to work with local water system managers and households to understand what was really going on. They did this by getting individuals to draw their daily water sources, which ended up being much more diverse than just the reticulated water system. And they observed two really important water technologies, this jug and this bucket, that were used by many of the households for different water sources, including groundwater, rainwater, seawater, and store-bought water. And so after discussing their common significance with local people, it was decided that these measures could then be used by local people to model how much water they were using and for what purposes and from what water source. Now, this is quite a common issue globally. If people are not using something from a formalised centralised system, then it often comes from a local or informal source and is not accounted for. So in terms of using these measures, here you can see the water model and data chunks of bucket and jug equivalents that were circulating through the Kiribati landscape as small beads. Now, although these measures are new, the basic data types, algorithms and calibration tools for setting up such low-tech water management decision support systems for informing the effectiveness of governance are not really that dissimilar to the processes used in many more computationally complex and automated intelligence systems for metrology and decision support in water systems. Complex system behaviour grounded in multiple interacting feedbacks between the environments, the people and technologies needs to be understood as an input to determining an effective course of action. And it's in thinking about these histories and the likely needs and desires for the future that brings me to the new cybernetics that we're starting to collaboratively outline at the ANU and with all of our partners. Developing means of critical thinking and doing for acting effectively in complex systems, including those where water is central. And this has never been more important as we think about all of the ongoing tensions with local water management, global geopolitics. So this new cybernetics will invariably involve the art of combining multiple knowledges from different places and situations and disciplines, including a range of technologies to understand and govern our water systems more safely, responsibly, and sustainably. And metrology is obviously a really big part of this, as well as the cultures it is developed in and the ways in which it informs our future decisions. And so having French and Australian researchers to discuss it today is a really delightful thing. And with that, I wanted to close in saying thank you, welcoming you to visit us in Australia in Canberra, and I'll hand over to Frédéric Jacquet, the AFRAN France Hub Leader, to chair our first session. Thank you so much again to everyone for your participation in and sponsorship of this event, and I hope you enjoy the webinar.
Thank you very much, Katherine. So let's kickstart part one. Now that we've had this wonderful introduction, so there'll be three presentations, three examples of innovative approaches in terms of metrology. I want to specify to our speakers that you should try and speak slowly, because when you are reading a text or speaking really fast, it's very difficult for interpreters to really do a good job. So we'll start with the excellent Rob James. He's going to tell us about a bespoke approach to hydrological monitoring using low-cost sensors. Rob, feel free to share your screen.
So I'll be sharing with you our bespoke approach to hydrological monitoring using our low-cost sensors. So we've got basically one example that we use at our Sunbury project, northwest of Melbourne. And it's just the way we do things. It's not meant to be any gold standard, but it's how we're moving at the moment. Next. There we go. This is our Sunbury project. So basically, we're monitoring the hydrological change that's caused by urbanisation across a water-sensitive urban design gradient. And so we're trying to detect these subtle changes in flow level. And we're using low-cost Arduino microprocessors as our loggers. And the system's and we're using LoRa and GSM to get the data back onto our server. And so our approach is to basically get an idea of the site challenges and also the data requirements. And so site challenges we're coming across in-stream vegetation, so that can make a difference on which type of sensor you choose to use. If they're difficult access or remote sites, maybe you want them more telemetered. If they've got a lot of algae, and then they may need to be visited more often. Slope and backwatering might also affect which type of sensor you use. And vandalism and theft. We generally try and make our sensors and loggers look as boring as possible, so they don't look attractive to steal or to break or anything like that for vandals. And the data requirements, we need to consider our accuracy and our resolution and range, and our calibration and drift, and whether or not we need to have our data telemetered, or whether we're going to be visiting these sites all the time, so we don't really need it anyway. Say for a short-term student project or something like that, we wouldn't bother. And make sure we've got the right time step. And so considering the time we have to be able to roll out this kind of a system, how much it's going to cost, and the quality we're going to need for certain sites, then we end up with our bespoke monitoring system. When we come to select our sensor, we've got a lot of options. So generally we're heading towards pressure sensors quite often, because we can use them in any water body. We can use them in monitoring bores, and they're not affected by in-stream vegetation or anything like that. And they tend to drift a little bit, but not too badly. Ultrasonics are great for open water. They don't drift because they use time of flight to detect how their distance down to the water, so it's out of the water. So, and they're not impacted by, because they are out of the water. Capacitance sensors we use sometimes. There are multiple different ways of having a capacitance sensor, like different designs. This particular one up on the top right is they measure capacitance along a cable that has like a Teflon coating, a coaxial cable, and the water level gives you a different capacitance reading. And so these can be good for the student projects or some of our projects. And the fourth one is laser, which we haven't had a lot to do with yet. I know Monash have been working with this a lot, but I'd like to learn a lot more about these. And so what we found is there's a big cost accuracy trade-off. So for our sites on the left there, we don't need millimeter accuracy, and so we can get away with cheaper sensors. So they're about $50 each, compared with the sites that are on the right there, our flow monitoring sites, which we really need to be quite good to be able to detect those changes in the hydrology. And they're probably about $1,500 each. So yeah, it's a trade-off between the both, and working out how many sites we're going to need as well. So yeah, this is one of our flow monitoring sites. So we install weirs, and you know, so there's obviously a bit of cost involved in setting them up, but they're quite important for our project. And so being this is a high value site, it's worth us putting in a more expensive pressure transducer. That's a hot pressure transducer. It gives us temperature as well. And but we're still using an Arduino and also Arduino gateway to send that data back and put it online. This is for our bore site. So for water level monitoring, rather than having to measure flow so accurately, we can get away with a little bit less accuracy in these sites. So that's our finished logger at the top left. It's not very exciting, but that's how we like it. And there's a little, not actually picked up very well in the photo, but it's got a small solar panel. It's only a 1/2 watt solar panel, but it keeps them going quite well. On the left, on the bottom, we have our calibration mesh setup. And so these sensors come already with an onboard temperature compensation, but we add other temperature sensors if we decide that that particular site, they need to be better. And then there's a photo of our installation on the top right, out in the forest. And then on the right on the bottom, we have a setup that we use for checking our data. So we go and take manual measurements. So we drill a hole in the side of the PVC pipe, and that's basically just a dipstick, so we can post-process our data. Yeah, and so our data's delimited. So what we found at a lot of our sites out at Sunbury, there are large gorges where we need to detect our water level changes. So even though it's quite close to Melbourne, we have no GSM coverage down in the valleys. And so we're using LoRa. So we're sending via LoRa radio up to our gateway. It's up the top on the plane where we do have GSM coverage. And from there, we send out MQTT data. That is, it goes straight to our Unimelt server. So once we get to the server, we use Node-RED, and Node-RED kind of like directs the traffic of everything. So it's sending all of those little packets of data into all the appropriate database tables for the different projects that we're running at the moment. They're all Postgres databases. And then we then query those databases with our Shiny, and that's an example of our Sunbury dashboard on the right with a bit of a hydrograph there. It also, Node-RED's handy for sending email alerts. So if you haven't heard from a certain sensor for a given amount of time, it'll we've got it set up to send us emails. And given that we've got a lot of sites, because we have cheaper sensors, we have more data management. And so we found MIT App Inventor to be quite good at making our own apps for the field notes, because the field notes are being collected by multiple staff, and we wanted to standardize our whole procedure. And so you select, you drag essentially blocks into your app, and then there's a back end that you can configure those blocks, and each block is got JavaScript behind it. And that's an example on the right-hand side of our comma-separated data as it comes in our email. When it comes in like that, we can then import it and match it directly to our flow and level data. And so we'll see where our manual check compares with our actual recorded data. So thanks heaps for Frederick Cherky, Kai James and Axel Balon. They've done all the development work. I've been wiring things together. So thanks a lot for listening.
Thank you very much, Rob. I guess we have time for a few questions. Alors, la première question, comment gérez-vous les variations
First
rapides?
question, how do you manage quick changes in water level with a pressure sensor?
I don't. They're generally not very quick variations in level, because like a lot of our flow is monitored behind a weir, so it's in a weir pool, and it's over 6-minute time steps and things. We don't have very fast, accurate. It's probably we take like 10 data points or so and average those out, and that's about it, but we found it smooth.
Okay, quick question. So 3 quick answers. How do you compensate for temperature with the ultrasonic sensor? How How do you manage that? Do you measure also the temperature for the compensation?
Yeah, we've been, this is largely, well, this has been all Frederick's work actually. So we had a look at what was where our biggest errors were coming from, and temperature was the biggest influence, and then to a much less effect was humidity. And so we ended up for robustness in dropping the humidity and monitoring for temperature with its own one-wire temperature sensor.
Okay, quick answer to this one. Who is cleaning the probes for fouling? Do you have inhabitants, or are you doing that by yourself?
Cleaning the pressure probes?
Yeah, any probe, yeah.
A lot. We haven't been cleaning the pressure probes. We've been taking our manual measurements and comparing our data, and our data has not been drifting to the point I think we needed. But we might find that in the next coming years we're going to have to deal with that. But they are extremely sensitive, so it's hard to clean them without breaking them.
Okay, and yes, no answer. Does these probes record conductivity?
No.
Okay, thank you very much, Rob. I guess we still are on schedule. So we will now move on to Aldrich Navratil, who will present about low-cost sediment transport monitoring. Aldrich, you can share your screen.
Well, hello, everybody, and thank you for inviting me to talk about this work that we've done together with all of the different partners, notably with the University of Melbourne. I'm going to talk to you about some examples of low-cost metrology for fluvial geomorphology applications to follow sediment transport in rivers. So when presenting this work to some foreign colleagues, they asked me about the low-cost aspect of the technology, and they wanted to know whether we worked on this low-cost technology because of a lack of financing in French research. And so this presentation is a kind of answer to that question. And so the aim is to look at the different challenges linked to low-cost metrology in environmental science, and especially to look at this application for fluvial geomorphology. So I'm going to show you that the advantage of low-cost technology is not just about economics and budgetary considerations. Now, in looking into this question, a low-cost technology applied to environmental science. So we looked at international literature, and for about 10 years or so, there's been an increase in scientific production focusing on smart environment monitoring and on the Internet of Things, so connected objects, and low-cost tools. So this was done by Pierce in 2020, and it showed that the different low-cost work, different low-cost technologies allowed to bring down costs by 92% compared with traditional devices. Now, of course, this is just the cost of instrumentation that is taken into account, not the cost of work and development, which I'll mention a little bit later on, which is still quite high. Now, these low-cost technologies rely mainly on Raspberry Pi devices and Arduino technologies. These have been employed in a certain number of studies to follow air quality, water quality, notably with our INRIA colleagues, rainfall monitoring, but also geophysical applications involving participatory science programs. And they've all shown that this low-cost technology makes it possible to multiply the number of measurement points. So this is what we heard about from Rob earlier on. So measuring points at a high frequency, providing better spatial and temporal resolution of changes to hydrological processes globally. Now, open source aspects also make it possible to start participatory science projects. That can also be interesting for the future. Now, as part of our research, we have been wondering about how to use these low-cost tools. So microcontrollers, for example, developing sensors, reusing sensors in order to follow the fluvial forms, their dynamics, the dynamics of rivers and sediment flow and particle mobility. So the mobility of particles in waterways. So we used Arduino technology. It's a platform for open source prototyping, and it allows users to create interactive electronic objects. Arduino was invented by Italian researchers for programming training in their classes. So we implemented, together with my colleagues, a certain number of tools developed on these platforms based on Arduino, on solar panels, in order to save on energy, batteries. We've got systems that communicate, systems that can send data on a regular basis, so little packets of data to a measuring station. And then we try to encapsulate that in a PCB, so that we've got to kind of plug and play Arduino tools. Now that data is then sent to a site, an internet site or an interface that allows us to view data every 10 minutes. So the system is refreshed every 10 minutes, and this allows us to follow different systems, changes, the systems themselves, and the environments that we're following. So it's something that's very advantageous, and that's something that was underlined by Rob earlier on. So our main constraints, what are they? Well, first, when it comes to the development of hydrologist kits, so to speak, well, we need to have something that's free and open source. It has to be accessible, but also economical. It has to be as accurate as possible, but of course, it needs to consider the measurement objectives. We don't have to be within millimeter precision for certain systems. So there's a balance to be established between accuracy and the objectives of our measurements. It's important to have adaptable tools, tools that can be transferred to different aquatic environments, rivers, lakes, groundwater, etc. It's something that has to be robust. You know, we're following hydrological systems that are subjected to droughts, so to floods. So the kit has to be very robust. But then there's the connected aspect as well that has to be taken into account. You know, different information will be sent on a regular basis about these systems so that quick action can be taken. So here are some examples now of low-cost technology applied to sediment flow, sediment transport. So this is seismic following of rivers that we're looking at now. It's a proxy that allows us to indirectly monitor sediment transport or transport, sorry, of pebbles using so we use a geophone. The signal is simplified and then integrated, and this allows us to follow what's happening at the same time as the flow rate. So that's in blue. So it's the Sèvres. It's a water course just below the écran. We've got the flow rate in blue, and then the seismic monitoring is shown in red, and that represents transport in the river. And we can see it of what's happening over time. So it's a tool that allows us to simplify the system. It makes it possible to have long-term monitoring, and that's important for fluvial geomorphology if we want to follow floods, which are by definition rare but also intense. So here's another example, this time based on the reuse of a sensor that already exists industrially. It's a turbidity sensor. It's something that you have in your dishwasher. So it's something that can be reused in river applications in order to monitor flows of suspended matter. So this is work that is currently being developed. There are 2 PhD students working on this subject with the university, in collaboration with the University of Melbourne. So here's another application. This focuses on monitoring. So we were talking about flows earlier on, sediment flows. Now we're going to talk about the flow of particles and monitoring that flow. So based on antennae, so that we can follow artificial pebbles and using an RFID system. So that's what we have in our credit cards, for example. So we've installed these antennae in water courses so that we can follow the artificial pebbles that go by in the flow of the river. So these antennae have also been installed on drones. So there are drone applications for river management. So when we install the antennae on drones, this means that we can reduce the costs of monitoring considerably in order to assess the transport of this sediment. And here's a last example then. So we've got instrumentation inside the false pebble, and this allows us to follow in real time with a high time resolution our pebbles. So traditionally, this is the Sèvres in the Écrin area. You can see the flow rate in blue, and traditionally we've got little red dots. These are the dots that we follow. They allow us to redetect the pebbles that have instrumentation inside them, and we can recreate the transport of the pebbles. And we've got several pebbles, and so we can assess the travel of these pebbles over time. Look at how they live in the river over the course of time. So this work doesn't mean that there is less monitoring work. There's actually more monitoring work. So it's not just about budget savings that these low-cost solutions are being used. These technologies actually make it possible to multiply the measuring points and to improve spatial and temporal resolution of monitoring in order to better identify hotspots and hot moments. It also opens the black box up of the watershed, so we can monitor different aquatic environments at different spots. It's something that for laboratory research makes it possible to reappropriate metrology in research labs and be really technologically innovative, so we can invent new things fairly quickly thanks to this technology. And it also means that we can share tools quickly, but also data quickly, so that scientists can dialogue with water managers and design or research and development offices, as well as citizens. So we've got a certain number of applications. We've got some case studies for CASPER, so which means sensor and participatory sciences. And so we can involve citizens in all of this research. So thank you for your attention. So Dave, I don't know if you want to share your screen. So for this first part of the presentation given by David McCarthy, we're going to hear about sampling methods for wastewater surveillance. So whenever you're ready, David.
Thanks, Fred. Very nice to be here, and thank you everyone for inviting me to present. I'm really excited. Yes, as Fred said, I'm going to be talking about sampling methods for wastewater surveillance, and in particular, we're interested in sampling at very small scale, so building scale and sub-catchment scale. Much of this work, though, is applicable outside of the wastewater pipe into your stormwater drains and rivers, etc. Lots of people to thank, no time for that. Lots of organizations to thank, no time for that either. Want you to just be introduced to the team at Bossel. We develop logger boards. This is our brand new nano board down the bottom right-hand corner. Super exciting. We do training courses. We've developed 8 different sensors turbidity sensors, velocity sensors, depth sensors, out of water radar sensors that measure surface water velocities, EC sensors, temperature sensors. We play around with different sampling techniques, and we play around with tipping bucket rainfall gauges too. And we host a yearly training course in Internet of Things for sensing in urban systems. Send me an email if you are interested. On to sampling methods. Different sampling methods are applicable at different scales. Sometimes in wastewater, when we're talking about wastewater and COVID in wastewater, sometimes we are interested in looking at where an infection comes from. Sometimes we're interested in just understanding overall community level infection rates. Grab sampling, which I'm sure you're all aware of, is good in some cases, but poor in others. Grab sampling may miss a pooping event of that one individual that has COVID-19 in our catchment. And so maybe not the best sampling method. Autosamplers are great. They can take some composite samples over time and therefore provide us with a daily average sample. Unfortunately, they are expensive and they're bulky and they take a lot of effort to install. We needed other methods that could do what we needed them to do at small scale throughout a huge urban wastewater network like this one shown here in Melbourne. Today, I'll be talking about 3 methods very briefly. Passive sampling, using the TORPOODO, as we called it, or the sewage sub. The MAD-AS, which is the MAD in-stream autosampler, and a portable qPCR system that we're testing. On to passive sampling. What on earth is this? Early records demonstrate that this was done in 1950, where someone attached a piece of medical gauze to a string and dangled it in a wastewater drain. And they came back 10 days later and assayed it for a pathogen called salmonella. Very interesting stuff. We use it today for tracking COVID in wastewater. We trialed many different ways of employing these passive samplers into the wastewater system. And we learnt a lot during these deployments. We then went to sites and we deployed them in very small situations. And those gauzes clogged up with all the yummy things that are found in wastewater. We realized quite quickly we needed to protect the gauze or the passive sampler from all of this yucky stuff. So we developed these boats. We thought they were perfect. No, they were not. Lots of clogging. We then settled on this concept of a torpedo-shaped housing. And indeed, we found that these housings were very good at avoiding too much clogging. So we started mass producing them. These passive samplers have very simple, they have a weight in them, and they have other little pieces of material that associate with the SARS-CoV-2 when they're dangled in wastewater. We sell them if you're interested. But if you have your own 3D printer, you can print them. And we've also developed minute ones that are just the size of your finger, and they can go into very small pipes, like the ones that come off your property. To date, we've made over 35,000 of these. On average, we calculated that there are 43 of these passive samplers deployed every day over the last 21 months. That's pretty good, I reckon. We've published a lot on these, and other people around the world are now publishing on this torpedo concept. I'm not going to bore you with all of the results today, but one important result was understanding whether there was a linear relationship between the accumulation on the passive sampler and the concentration in the wastewater. Lucky enough for us, there was. Beautiful relationship, quite a wide scatter, but for microbial assays, pretty good. I want to move on to another innovation from our group called the MAD-AS autosampler. It's an in-stream autosampler that sits in the water. Water goes past it, it samples, and water gets put into the tube that holds it in place from the surface. They cost almost nothing. It contains a peristaltic pump that is 3D printed with a brushless motor and a little board that we designed called the Bossel Micro, and some batteries. We decided the first thing we should do is compare how this system worked against an autosampler, like the Huck autosampler you see in this picture. And we did this in many different situations. We did it in wetlands, rivers, creeks, stormwater systems, and in particular, we did them at wastewater treatment plants. This graph is just one of the comparisons. On the y-axis is the MAD-AS autosampler composite. On the x-axis, it's the Huck autosampler. As you can see, very good and very relatable concentrations from both of these machines, one costing $25 and the other costing multiple thousands. We've already got remote triggering in place as well for this MAD-AS, which is pretty cool. And we've tested it under a meter of water and it works well. So we can trigger these MAD-AS autosamplers remotely, even though they are submerged. Next steps, we're integrating a flow-weighted sampling approach using our out-of-water radar velocity and depth sensor. And our next thing is to develop our discrete autosampler. Prototypes are in place where we can take discrete samples over hydrographs instead of just composites. If you're interested, lots of information on our Bossel site. Finally, very close to the end, we have nothing to do with biomeme, but there's this thing called a portable qPCR machine. You can go to site, take a water sample, extract the RNA or the DNA from that sample in 5 minutes, put it through a battery-powered portable qPCR machine, upload the answers automatically to a cloud server for someone else to interpret. And we've been using this for about a year now on SARS-CoV-2 assays from wastewater. Absolutely an amazing machine if you're interested in this type of technology. If you'd like further information, please head to any of these links. I'll post my PowerPoint if possible via Fred. And if you want, you can also send me an email, david.mccarthy@monash.edu. Thanks very much.
Great presentation, Dave. Thank you very much. There are few questions. Maybe the one that you can answer now is what pollutant can you monitor? What kind of pollutant? Can you do heavy metals, hydrocarbons?
With the MAD-AS or with other?
I guess with any of the system you have, what is the range of pollutant you can?
Good question. We monitor with our sensors. We monitor EC, so electric conductivity, temperature, depth, velocity, turbidity, and we're looking into ammonia sensing, DO sensing, and a few others. For our MAD-AS, we focus on microbes, but we've also tested it for total suspended solids and nutrients. Not very good for things like hydrocarbons because our storage is a plastic tube, but working quite well for heavy metals as well.
Thank you very much. We will move to the second part of this webinar, and I give the floor now to Jean-Michel for the chair.
Oui, bonjour à tous. Très heureux d'être parmi vous.
Yes, hello everybody. I'm delighted to be here with you. So to be quick, this second part is all about UAVs or drones. So they've started to appear and be used about 10 years ago. They're used a lot by scientists to acquire data. So I'm going to give the floor to 3 scientists that are passionate with drones. I think these UAVs can only be used by people who are passionate and who love playing with them. So Raphael, who is going to speak first, how can we use UAVs to move on in hydrology? Yes, thank you very much. And thank you, Jean-Michel, for this quick introduction. My name is Raphael Antoine. I'm a geophysicist at Cerema. I'm particularly interested in hydrology, and I've used UAVs since 2016. We use UAVs a lot in our team. I'm now going to talk about geohazards. So how can we use UAVs when monitoring water-related geohazards? So ground movements, gravity flows, sinkholes, and monitoring floods, whether they be associated with river floods or coastal flooding. So there are several terms being used internationally to refer to drones. So you'll find UAVs, UASs, unmanned aircrafts, RPAS. So they all refer to the same system. So it's an unmanned aerial vehicle. It's pilotless, and it is controlled remotely, either totally or partially, or can be fully autonomous. So that is the definition of the International Civil Aviation Organization. So you have very small ones that are only a few centimeters big and that have fairly low autonomy, and you have much bigger ones that can actually fly for days. As Jean-Michel mentioned, the use of UAVs has gone through the roof over the last 10 years, so really exponential development. They make it possible to capture photos and videos from a high altitude. So that's the first use. They're extremely flexible and quick, thanks to miniaturization of sensors and progress made in terms of autonomy. You have commercial UAVs that can fly for hours with several gigas, and they can enable easy location because there are now embedded geolocation systems that are very precise. So what do we use them for? Well, we can do 3D modeling of objects. There's a method that developed a lot over the last 10 years, which is based on photogrammetry, which makes it possible for you to reconstruct a surface. And that photogrammetry method has helped us make huge progress. And the use of artificial intelligence. So there's also advanced geographic information system. And now, more recently, artificial intelligence has been used more and more. I was telling you about miniaturization of new sensors. They are either optical, LiDAR, thermal infrared, so thermal cameras. And in the future, these drones will be the link in the chain between satellite data and more traditional ground data or airborne data. So that's what's in store for us in the future. So let's move now to how we can use those UAVs to monitor ground movements. So first, a few applications that you can find in the literature. Drones are used for mapping hazards. They're used for morphological analysis, for kinematics, for volumetric changes, or to detect cracks. To that end, we'll use mostly two types of systems, optical or LiDAR systems. Visible cameras are used a lot. LiDAR systems can help get clouds, dot clouds, and thermal cameras are not as much used, but they can help get complementary data. We can reconstruct the surface in 3D using photogrammetry, and we can also do 3D model comparison and even do image correlation. And we use also particle image velocimetry to compute and try to predict ground movements. This slide is an example of an application on a wharf in Le Havre in Normandy. We developed two surveys above wharves. There we knew there were cavities forming underground, fine particles being depleted, and the formation of cavities over several years. So next slide, please. So you see that we've used a UAV that has both a visible camera and a thermal camera. So we used an automatic flight plan, and we used photogrammetry and pictures. So this is what we got thanks to the visible camera and photogrammetry. So in blue, you have a low altimetry that highlights the formation of cavities at the level of the surface. So 4 areas here where we see that the ground is subsiding. Here, it's one of the thermal camera images that we acquired on this wharf. This thermal camera image was acquired around 1 p.m., 2 p.m., and we spotted thermal abnormalities, which reveal surface formations that we were able to link to evaporation, and that preferential evaporation was generated by a more permeable system at the level of these formations. This is an image at 1 p.m., 2 p.m. We also captured images earlier in the day, and we realized that the signal was completely drowned in the thermal noise of the surface, which demonstrates that to use the thermal camera, you have to acquire images through the day, at different times of the day, so as to be able to detect a thermal abnormality associated with that type of distortion or formation. Here, you have an example of the use of UAVs for coastal monitoring. There are several observatories in Normandy, Here you see pictures from the Daniell Observatory, which is near the Black Cows site. I would recommend that you go have a look. It's very beautiful. It's in Normandy, in Villers-sur-Mer. So it's a clay formation, and there's a very active landslide, coastal landslide. So we use UAVs to try and monitor the evolution of that landslide. Next slide, please. So we're going to do 3D models. So on the left-hand side, you see a 3D textured model of the Black Cows landslide with ridges and valleys. So we use 3D models. We acquire pictures and do 3D modeling. We now have about a dozen 3D models of that landslide that we've acquired over the last 4 years, and we can then compare. And we can calculate the distances between these different models. And this way, we can determine where sediments have accumulated or erosion areas. So we can thus determine more specifically deposition areas and erosion areas. And we can actually calculate volumes of erosion and of deposition. It's not simple to do, but we're starting to get better and better at quantifying these morphodynamic aspects. Raphael, can you move on to your conclusion, please? Yes, of course. So I'll skip over this slide. Just want to say a few things about this slide. Thanks to 3D modeling, we are able to integrate it into geophysics, and we can thus get very interesting images of the subsurface that integrate topography. Jean-Michel, can you flick the slides? Mustafa will tell you about this project. Yes, I wanted to wrap up by telling you about this project. It's the WACA project, the West Africa Coastal Areas Program. This project is dedicated at supporting local communities to foster resilience faced with coastal floodings and help them have better stewardship and management of their coastlines. I was in Sao Tome a week ago to provide a training course. So to train people in methodology of using drones for coastal monitoring. In Sao Tome, it's very interesting because they have no access to satellite data because there's always a lot of clouds on that island. And the only way to actually do coastal monitoring is by using drones, UAVs. So this is a concrete example of how we can use UAVs for coastal flooding monitoring. Sorry, I was a bit long. No, that's fine, Raphael. So there are questions in the chat. And if you want to share a video, you can put it in the chat. 2 quick questions very quickly, maybe to contextualize. If I want to do river flood monitoring, what kind of UAV can I use, and how how accurate can you get when it comes to ridge breach or cliff breach? Well, in terms of autonomy, a lot of progress is being made. So you can use it for an hour. How many miles or kilometers? Well, we are able to cover 5 to 6 kilometers a day with small UAVs. Small UAVs that do not have a very long autonomy or battery life. So, but what you can do is buy several batteries and use and so you can monitor for longer. But an hour is very easy to find in terms of battery life for UAVs. And this and about your second question. In terms of accuracy, so we are down to the centimeter. So 1-2 centimeters in XY and 2-3 centimeters in Z. So it's very accurate. Okay, thank you for this very specific question. Raphael, thank you very much. I'm now going to give the floor to Katherine Russel. We talked about low-cost sensors. We're now going to talk about open source. So still the same rationale to be able to share data at a low cost. Katherine, over to you.
Thanks, Jean-Michel, and thank you all for having me. My name's Kathy Russel. I'm a research fellow at the University of Melbourne. I collaborate with Frederic and Aldrich on low-cost sensors, but today I'm going to talk about another aspect of my work, which is about geomorphologic survey and methods for processing that morphologic data. Okay, so I'm not a drone expert, but I'm a drone user, and I just want to share some of the things that I've been doing with drones. Our use of drones really goes up this scale from the more basic, cheap, easily deployed, easily processed, all the way up to the more specialized drones. And so I'm working a lot in the space of visible photography drones. So these are the most basic drones, low cost, no special processing required, but they allow us to get much better access and to inspect our sites on a different scale. So for example, if I'm standing on the riverbank, I can get my drone up into the sky and I can see the valley context, the floodplain, and get that broader context of the river. If we move into more specialized sensors, we can use sensors like multispectral sensors. These are used a lot in agriculture and in forest ecology. So we can look at things like vegetation, riparian vegetation boundaries, water boundaries. We can look at water quality that's related to optical properties of the water, so turbidity and color. And so this really gets into that more interdisciplinary work. Then as we move up the scale, we get into the methods that can produce terrain and elevation model data. Photogrammetry requires, can be done with those more basic photography drones, but requires them to have a high precision GPS and specialized software to process the data. And so you have software that will take overlapping photos and run pixel tracking algorithms on them to produce elevation models. And then you move into LiDAR sensors, which require a more specialized sensor. Generally, you need a larger drone to carry that payload. And then you get into the territory of needing special pilots licenses. So just a little bit more complicated. So for me, I'm working mainly in that photogrammetry and visible photography space. But once you get this elevation data, then you can use it for direct morphological interpretation. You can use it as a basis for hydrodynamic modeling.
And you can, if you repeat those surveys, then you can detect geomorphic change. As Raphael said, they're a really useful intermediate between those large-scale satellite or aircraft observations and ground-based observations, where, for example, if we're relying on aircraft-based LiDAR data, we're generally relying on government acquisition programs, which tend to run every 5 to 10 years in most places. Whereas if we use a drone, then we can get much more rapid deployment. We have flexibility in how and where we get our survey data. We can repeat the survey multiple times if we're trying to track a rapidly occurring process, and they're much lower cost. So I just want to take a little bit of a sidestep from that and talk a bit more about how we get geomorphological insights from this unstructured data that we get from the drone. So we're getting out images and terrain models. How do we turn that into something that, that we can interpret? So there are a lot of examples of this. There's geographic object-based image analysis, which will classify images into similar segments, and then can be interpreted as morphological units. You can digitize directly from that data. You can run hydraulic models. But I wanted to share some of the work that we've been doing, developing some open source methods to extract morphological attributes of rivers from terrain models. The problem that we're addressing is identifying bankful channel boundaries. This is a hard problem in geomorphology, and a lot has been written about it. There are different definitions of bankful, what features you're looking at that indicate the top of bank. And even when you agree on a definition, it can be difficult to identify the top of bank, whether you're in the field or looking at remote sensing data. But it's a really important first step for a whole range of other morphologic analyses of rivers, for things like habitat mapping, for identifying in-channel geomorphic units, for doing hydraulic geometry assessments. So we tested and compared two approaches that had really different paradigms. One was an objective method, which optimizes a objective function, which is built based on a strong conceptual model, which comes from theory. So in these methods, we give the model much more information about what to look for. So we tend to give it more of a spatial framework. We define the center line of the stream. We create cross sections perpendicular to that. And then we extract the data for each cross section, and we run a model cross section by cross section. And on each cross section, we can process that, the elevation data, to give us variables that will indicate where the break of slope is at the top of bank. So that could be hydraulic depth or the width depth ratio, among others. The other approach that we tried was a learning method where you can train an AI to learn where the river boundaries are, based only on training data that you give it. Those methods work directly with 2D images, so they don't need as much of a spatial framework to begin with. And we used an example there of learning methods, which was a convolutional neural network. So the objective method that we applied was based on this work by De Rosa et al. In 2019, which maximizes the hydraulic depth for each cross section. The hydraulic depth is the wetted area divided by the wetted width. And so as the water level increases in a cross section, the hydraulic depth increases until it starts to spill out over the banks. And then the width increases greatly while the area doesn't increase as much. And so that function will be maximized. We made some adjustments to the de Rosa model because it was developed on large rivers. We wanted to apply it to small and complex streams, so streams that had been through a lot of incision processes, streams that had natural levees, and the original model didn't work so well for those. The other method that we applied was a convolutional neural network image segmentation algorithm. So we undertook transfer learning on this model, which is where you can retrain a model that is already trained to recognize or to segment images. And then you provide it new data on the problem that you are interested in. And it will learn to recognize those particular features. So we used the ResNet 18 model and then started feeding it rather than the red, green, blue photos that it's usually trained on. We started to feed it terrain data. And so we were giving it elevation, slope, curvature, hillshades, all of this information that we would generally use as humans to define where the top of bank is. And I'll just share some quick results. So we found that the HydXS, the objective method, outperformed the CNN overall. But they performed differently in different reaches of our study area. So the HydXS was much better in the smallest channel, which was a small constructed drainage ditch, where the CNN wasn't able to recognize that as a channel. The CNN outperformed HydXS in the larger and more complex channels. And the biggest difference between those types of channels where the CNN performed better was that they were incised channels that had been through a process of evolution in the past. So they had incised and then recovered, and they had these inset channels and benches. And our objective method was only able to recognize that first bench as the top of bank, whereas our expert delineator had identified the top of the macro channel bank as the top of bank. And so the CNN was better able to replicate that. Just to sum up, we are continuing to develop this method, but it's also really important to us to get it out there and usable by other researchers so that it can be developed in many different places and tested across many different places. We, in turn, benefited a lot from previous open source development by de Rosa 2019 and the ResNet 18 CNN. And so we're intending to make these tools available now as researcher grade open source packages and to publish on them in the next couple of months. Thank you very much. I'd love to answer any questions. I did this work in collaboration with a lot of people and my email is there.
So these are extremely interesting tools that really add to the data taken by drone. We've got some questions. How many images, field images, terrain images, and models do you have in your database?
So for the convolutional neural network training, it was a reach of about 15 kilometers length and had 5 different reaches with different properties. So we gave it a bit of diversity in channel types that it recognized. So I think that it takes 256 by 256 meter images. I can't remember exactly how many, but that's an indication of the total amount of data that we used to train that model. When you're using this kind of transfer learning, you don't really need a huge amount of data to retrain the model.
D'accord. Moi, j'avais une question.
Okay, and here's a question about the end use of the data that you use. So conceptually, you have a monodimensional approach based on cross sections of the river, and then you obtain 2-dimensional data with images, so using photogrammetry. do you plan to use hydrodynamic models afterwards in order to add things afterwards?
This whole process was very problem driven, that we are trying to build big hydraulic geometry models across the whole of the Melbourne region. And we found that the data that we had available was really low quality. So we started to develop these new processes to extract better data. So that's the motivation, but then the usage of it, I'm starting to see some real potential for some hydraulic metrics to come out of this. Because we're looking at urban streams, it's really interesting to me to look at things like stream power and sediment transport capacity in these streams and how they change or how they're altered in different parts of the stream network. So yeah, we would like to start to extract those hydraulic properties as well. But yes, the data can be used directly in hydrodynamic modeling as well.
Très bien, merci beaucoup, Catherine.
Great, thank you very much, Catherine. That's great. I think that the other teams will be able to talk with you about what they do. So it's really very complementary. I'm now going to hand over to Mustafa, who's going to talk to us about the use of drones to obtain data about dikes. Over to you, Mustafa.
Bonjour.
Yes, hello.
Bonjour à tous.
So hello everybody.
Mustafa Kasbari.
So
Je
Mustafa
suis
Kasbari.
docteur en
I'm a
sciences
doctor
microélectronique et systèmes
in
autonomes.
microelectronics and autonomous
L'approche que je vous
systems.
présente est un petit peu
The approach that I'm
différente
presenting to you is a
de nos
bit
amis
different
scientifiques qui ont pris la
from
parole
what
avant
we've
moi, puisque
seen
l'idée était de
before
vous
with previous
montrer un
speakers.
petit peu une
I'm going to,
orientation
it's focused on
business de l'utilisation
business
des drones
and the
pour
use
la
of
surveillance de digues.
drones for
Donc,
monitoring
je ne vais pas faire de
dikes.
science, vous le faites beaucoup mieux que moi.
So I won't
Vous
give you any scientific
tous les jours.
information because you're
Donc, quelques mots
scientists.
d'abord sur l'entreprise.
But let me tell you
On
about the
peut dérouler
company.
les slides, les premiers
So we
accessoirement
can
assez rapidement. Je sais pas
go
qui a la
through the
main.
slides. I don't know who's in control.
Alors,
There we go.
Atexis, c'est une entreprise que j'ai fondée il y
So
a
at
déjà 15 ans
Texas, I
et qui a
founded
une
the
approche
company 15
originale
years ago. It has
qui
an original
nous
approach
permet après de faire
that allows us
les prestations que je vais vous
to
présenter.
offer the
Les deux
services that I'm
premiers
going to present
piliers
to
sont
you.
ce
The
qu'on
first
appelle
two
l'approche
pillars
intégrée et l'approche marché.
are based on
C'est-à-dire
the integrated approach and the market approach.
qu'on a
In other
l'ensemble de la chaîne
words,
de valeur pour
we
pouvoir
have the whole
utiliser les
value
drones dans
chain
un milieu
so that
de
drones can be
service.
used in a service
L'approche marché,
environment.
c'est qu'on
The
construit nos
market
solutions drone
approach
sur
is
mesure en
that
fonction du
we
besoin des
make
scientifiques
bespoke
et des clients. Et tout ça est orienté
drones for
vers ce que j'ai
specific
appelé
uses.
l'approche
And
service,
all
le
of
drone as a
this
service,
is based on a
c'est-à-dire
drone
qu'on
as
ne
a
vend pas
service
nos
approach.
produits,
We
mais on
don't sell our
déploie des
products,
prestations de
basically.
services
We
pour
use
nos partenaires et pour nos clients.
service-based
Sur deux
solutions for our
slides très
partners and
rapidement,
customers. So very
l'approche
quickly,
intégrée,
let me
voyez, nous
just go through the
disposons
integrated
de
approach.
l'ensemble des
So you can
moyens
see that we've got
nécessaires
all of the
pour
means necessary
produire des services clés en
for
main, deux centres
building
d'essai en France,
bespoke
un du côté de la
services for
Nouvelle-Aquitaine, un du
France.
côté de
So that we've
Var,
got two
des
flight centers
espaces
in
aériens
France, in
réservés et
Angoulême
des
and Première,
laboratoires, des ateliers,
reserved
tout ce qu'il
airspaces,
faut pour
realistic
fabriquer les
test
drones
areas,
dont on a
everything,
besoin.
labs, workshops, and
Donc, on ne
lab
travaille
labs,
pas avec des
everything
drones du marché.
needed. So we
L'approche
don't work with
marché,
market
c'est
drones. The
partir
market
du
approach,
besoin du
it's
client,
about starting with the customer's need,
intégrer des technologies
integrating
dont on dispose
the
pour
technologies
fabriquer la
available
solution
in
clé
order
en main,
to make a
design jusqu'aux
made-to-measure
essais en vol.
solution,
Et tout
look
ça
at
a
the
servi à
design
quoi?
for
Tout
the
ça
user.
nous permet d'offrir
And this
des
allows
services
us
clés en
to
main
offer
slide suivant,
made-to-measure
avec
services,
nos différentes technologies. Donc,
bespoke
vous voyez,
services
on
with our
a en
different technologies.
propriétaire des
So you
drones
can see
qui
that
vont du drone de
we
quelques
own
kilogrammes
drones that
jusqu'aux
weigh
drones
up
de
from a
plusieurs
few
centaines
kilograms
de
to
kilogrammes, des
several
multirotors, des
hundred
hélicoptères ou des
kilograms.
avions.
So we've got different
Autour de
types of
cette flotte technologique, on a construit une gamme de services.
unmanned aerial
Et ce que
vehicles.
nous déployons
So the
sur le
drone
marché, ce
as
sont
a
des
service.
services clés en
What
main
we
utilisant ces
offer the
drones.
market
Slide
is services
suivant.
using these
Pour illustrer,
drones.
vous voyez, c'est très simple.
So
Des
it's very simple as you
technologies
see
de
on
la
this next
formation,
slide.
un centre d'essai
So
en vol,
we've got
des centres d'essai
technologies,
vol.
training,
Tout ça nous
test
permet de
centers. All
définir
of
un
this
bouquet
allows
de
us to
services,
define a package of
surveillance
services,
sécurité, transport,
surveillance,
logistique et data
safety,
collection.
transfer,
Donc,
logistics,
selon
and data
on essaye de
collecting.
faire sur le marché
So
de l'eau ou de la surveillance
whether
de
we're
digues
working
par,
on
par,
water
par
or
des drones,
on
ce sont
dikes,
déployer des
dike
services clés
monitoring.
en main
So we're
auprès de
talking about
scientifiques,
bespoke
auprès de
services for
partenaires
scientists
je dirais,
and
commerciaux pour l'acquisition de ces données.
commercial partners so that data
En
can be
slide
acquired.
suivant,
On the next slide,
il y a 3 types de
there are
use cases
3
que nous avons
types of use
identifiés sur
cases
lesquels nous
that
nous
we have
positionnons, qui sont
identified that correspond to
l'inspection
our position.
régulière, la
So regular
surveillance régulière
inspection, so regular
d'ouvrages,
monitoring of
petites digues, la photo de gauche,
dikes, for example, that's what we're seeing on the left-hand side,
des
on the
analyses
left-hand
qui
photo,
permettent la
analyses
prévention
that allow
avant
for
rupture, avant accident ou
accident
avant incident.
prevention, so
Donc
before
là, c'est
anything
plutôt
happens.
de la collecte de données
So
qui
it's
vise
about
à
data
être processée
collection
pour faire de la prévention.
so
Et
that prevention
puis,
can be
dans le
possible.
pire cas, des
And then in the
déploiements de
worst
solutions
cases,
drones pour de la
drone
gestion de
solutions can be
crise,
used in order to
ou
manage
du management de
crises.
crise une fois que
So
nous sommes dans
once
ce type de
the
situation.
event has happened, for
Donc les deux
example. So the
les deux
first
premiers use cases
2
concernent
use cases
des inspections régulières
concern regular
d'analyse, de
inspections,
suivi et de prévention, pour du
analysis
management de
and
fonctionnement
monitoring and prevention
d'infrastructures. Et la dernière, c'est
of
de
different
l'intervention
facilities, different structures.
ponctuelle pour du
And the last
management de
one
crise.
concerns on the
Slide
spot
suivant.
crisis
Dans le cadre d'un
management.
projet que vous
So next
connaissez bien,
slide.
qui s'appelle
So this is a project that you're familiar with.
d'hydro,
It's the hydro
nous
project.
avons étudié
So we
avec des
studied
scientifiques,
with
Cossart,
scientists,
Cerema,
Fistas,
et
Cerema,
d'autres qu'on
and
verra tout à
others,
l'heure.
and we'll go through the names later.
Comment intégrer des
How
capteurs
it
sur quel
would be
type
possible to
de
integrate
capteurs
sensors
et quel
and the
type de
kind of
drone
sensors and
afin
the
de
kind of
déployer ce
drones
qu'on a appelé le
involved in order
DIDRO,
to
qui est un
deploy
outil
this
intégré de
tool,
surveillance des
which
digues
is an
par drone.
integrated tool
Donc,
for
ce qui en
dike
ressort,
monitoring.
c'est que
So
3
what
types
comes
de
out
drones
of
paraissent
this is
nécessaires
that
au déploiement
three
sur ces
types
3
of
use
drones
cases.
are necessary for the
D'abord, des voilures
deployment.
fixes qui
The
vont
fixed
permettre
wings
de traiter de
that
grandes
allow
distances
us to process large
et de grandes
distances, long
surfaces
distances and
avec
large
des
surface
petites charges
areas
utiles,
with
des
small
multirotors qui vont
payloads,
nous permettre de travailler sur des
multi-rotors that
petites
allow us to
surfaces
work
avec
on
des charges
small
utiles un
surface
petit peu plus
areas
lourdes et à
with
très basse
smaller
altitude.
payloads
Et
and at
enfin,
low
des drones de type
altitude.
hélicoptère.
And then
Donc, on est toujours sur
helicopters.
ce qu'on a
So
décrit tout à l'heure.
again,
Il y a
we're
deux
talking
présentations en
about
arrière, des systèmes autonomes
autonomous
ou
systems
pilotés à distance, mais non habités, donc des
controlled
hélicoptères drones,
remotely. So
qui cette fois vont
different
permettre de
types of
porter des
unmanned
charges
aerial
lourdes,
devices.
plus de 5
So
kg, avec
helicopters
des
can
très grandes
have
autonomies,
big
jusqu'à
payloads with
4 heures,
and they
et
have
des très
a
grandes
long
élongations.
battery life and
D'un
they
point
can
de vue
cover
capteur,
large
ont été
distances.
sélectionnés dans le
So
programme
from a
slide
sensor point
suivant,
of
dans le
view, if we
programme
look at the
d'hydro,
next slide,
sélectionnés,
let's look at the hydro
intégrés et
program
testés, sont
and
ces
look at what's been
4 types de
integrated and
capteurs.
tested.
Des caméras
So we've
multispectrales
got
visibles,
multispectral
proche
cameras that are
infrarouge,
visible
pour
for near
analyser des
infrared in
situations
order to analyze
d'infiltration
situations,
d'eau, des caméras
infiltration of
thermiques
water,
du
thermal
type de celle qui est présentée
cameras
là en 75
like the ones
750
presented
nanomètres jusqu'à
here, so
1,5 micromètre,
750
du
nanometers or
lidar
1.5
pour des
micrometers,
nuages de points, de la
lidars
photogrammétrie de
for
précision,
point
pour
clouds
faire des
and
analyses de topographie
highly
de
accurate
précision,
topo
et enfin
analysis,
de la dépose de
and then
capteurs physiques, de sondes
light
déposées
physical
grâce à des systèmes
probes
drones et qui vont permettre dans le temps
that
de
allow
suivre les
over
évolutions de la
time to
topo
follow
à distance
evolution
grâce à ces capteurs qui sont positionnés sur
topographical
l'ouvrage.
changes
Donc le
based
travail
on sensors
scientifique
that
qui
are
est fait
placed
avec ces
on the
capteurs-là a été
infrastructure.
présenté avant moi dans le cadre des présentations précédentes. Un petit sur le slide suivant.
So I won't repeat what has already been touched upon by the previous speakers. Here is a summary, and many thanks to Jean-Luc Sora for this
cette image qui est
diagram.
un des résultats du projet d'hydro. Vous
One of
avez
the
l'ouvrage
outcomes of the
digue
Didro
vu en couple, et on voit comment est-ce que le drone peut
you have a
intervenir de
cross-section
différentes
here, and you
manières
can
grâce
see
aux
how
capteurs que l'on vient de
the
voir, et
UAV
grâce aux drones qui
can
ont été
be
décrits,
used
ou par des
thanks to the
systèmes
sensors that
de
we've just touched
vision
upon,
de haute
or
précision dans le
thanks
visible, dans le
to
proche infrarouge ou dans l'infrarouge. Là, on va
highly
travailler
high resolution
on va analyser des images comme
viewing
les
systems.
scientifiques avant moi l'ont présenté.
and that gives you images the same as what the former speakers told you about. So it can help determine the geomorphology of the levee, the dike. You can place the sensor on the flood defense structure and measure over time. You can also perform samples in the river, and we can have drifting sensors as well that can give you positioning and velocity data. Top right, you see one of the helicopters. It's the drone links Acknowledgments with thermal and infrared and visible cameras. Here is an example of work that was presented in 2019 as part of the DIDRO project, images that you're familiar with and you can analyze way better than I do. So it's a digital terrain model. Thanks to photogrammetry, we can reconstruct it, and then you have the use of the thermal camera, and that helps us pinpoint and spot an area of resurgence that is simulated by watering at that specific point of the dike. So using these three types of drones and three types of sensors, we can thus deploy a whole range of services. A short clip for you now.
Vous montrer à quoi ça peut ressembler
so to show you what it looks like in real life.
4 heures d'autonomie.
This helicopter has a battery life of 4 hours, 8 kilograms of payload, can fly in daytime and in nighttime, and that same helicopter, in the specific example, can actually drop a drifting tag that is going to feed you data of velocity.
On peut également venir déposer ce qui s'appelle chez nous le capteur quadro. Donc là,
there's also the quadro sensor, so it is dropped below the surface, you see, so it's an automated syringe that can actually make samples in a fully automated manner, and regardless of the weather conditions, even if it rains or there's a lot of fog, we can still use these systems. So I know that I'm out of time, but just want to touch upon one more point. You said several times that one of the difficulties associated with a UAV is to comply with the regulation so as to really make the best use. And I want to talk about the technology and the difficulties we ran into in the past for remote control. If you look at the top left picture, we've developed trackers so as to be able to really track these drones in full compliance with the regulation. That makes it possible to now deploy these UAVs at a very long distance whilst complying with all safety rules, and that gives you 24/7 service in the best possible conditions. So top right, you see the tracking. Bottom left, that is a short range tracking in the hand of the pilot, and that can enable long range, long distance service. So you can now deploy at a distance of 150 kilometers a fully automated service for 4 hours. Thank you very much for your attention. Yes, thank you very much, Mustafa. So from design to operational use, so much can now be done with using UAVs or drones. And what you touched upon towards the end, which is long range use, we have to factor in regulation. In France, we have a fairly stringent European regulation, so it'd be interesting to compare with Australia. Is it difficult or pretty easy to use that kind of UAVs on long distances? Well, for example, it seems to me that we can get pretty accurate, pretty precise data. I was trying to find out what those terrain digital models could give us in terms of accuracy. So in terms of vertical precision, can you give us an idea
Sur le positionnement vertical du drone, sur
on
des grandes
vertical
distances,
positioning
on a
of
deux
the
manières de
drone
faire.
on long
Ou on
distances?
vole
There are two ways
sur
to do
du
it.
GPS entre
Either
guillemets de
we use
précision, et là, on a des précisions qui
GPS,
sont très
and
exceptionnelles puisqu'on est de
that
l'ordre de
gives
25
us
cm. Ou on
25
vole sur du linéaire avec un
precision,
télémètre
or
laser,
we
ce que
use
l'on
a
fait aujourd'hui.
laser
Et là, on a une précision centimétrique en Z.
telemetering. And that gives us really a centimeter precision on Z. Well, I think we can go on exchanging in the chat, but it's high time we gave the floor to Dr. Nathalie Simonel-Amar from the embassy to tell us about what's coming next. So, Nathalie.
Good evening or good morning to all. My name is Nathalie Simonel, and I work at the Embassy of France in Australia. My work is, I'm sharing my screen at the same time. Can you see it? And so the embassy has put in place a set of programs supporting the initiation or the strengthening of research and innovation collaboration between France and Australia. These programs are seed funding programs and address the specific needs for collaboration of students, researchers, and multi-actors. And if the first development are successful, this seed funding can lead to more ambitious and structured forms of collaborations, such as the CNRS or inter collaborative schemes, or French, Australian, or European funding. So first of all, for student mobility, we have different programs. The first one is the Nicolas Baudin programs. It is dedicated to bachelor and master or PhD students, and it has 3 streams. The general stream supports the mobility of students from Australia to France, either in the framework of an exchange program or for students enrolling in an entire degree in a French university. It takes the form of a travel grant to cover the international travel expenses. The second stream is the Internship in France initiative. It proposes research internships in France or for Australian students. The objective is to create pipelines linking academia and industry. So these internships are co-funded by the French Embassy, the French host institution, the Australian home institution, and the industry partner. And many organizations have supported this initiative, such as Naval Group, Thales, Total, Airbus. The last stream is the Internship in Australia initiative. It has been created with the support of the 2090 South Australian government, and it should continue with the new government that has been elected recently. It offers a similar opportunity, but this time for French students to do an internship in Australia within the University of the Group of 8, Flinders University, or University of South Australia, and with Naval Group or Thales as the industry partner. Another program for students is the short program or summer schools. It supports summer school style programs and workshops, which are jointly set up by French and Australian research and education organizations. This initiative will grant up to €4,000 for each project. Its objective is to encourage mobility and collaboration. So that was for students. Now we have programs as well for PhD students and researcher. And this is the FASIC program. It is PhD, which means the program Huber Korean. It is a program that France has put in place with many countries to foster international research collaboration. And the FASIC, or French-Australian Science and Innovation Collaboration, is the PhD specific to Australia. It will support excellent joint bilateral scientific projects, co-designed by French and Australian teams, and co-funded by the FASIC program and the Australian Institution or Research Laboratory. It also has 3 streams. The FASIC PhD program supports the mobility of the PhD students from France to Australia or from Australia to France. The FASIC researcher program supports the mobility of postdoctorants or researchers, but only from France to Australia. And the FASIC workshop program supports the organization of jointly designed workshops in France or in Australia. This program aims at promoting future bilateral research networks, but also at initiating the development of international joint structures. And when relevant, it also aims at industry engagement with the academia network. We also have other programs. In specific area of science. So the SAF program is a program to foster research collaborations between France and Australia in nuclear science and engineering in the fields of human health, environment, and nuclear fuel cycle. The program will support early career researchers at PhD and postdoctorate level to expand research and innovation activities and to initiate sustainable research network and linkages to support Australia and French research and innovation. We also have a program in social sciences. So this research funding program set up with the Academy of the Social Sciences in Australia will support and reinforce social sciences collaboration between Australia and France through research activities on a topic of interest to both Australia and France, provided to eligible French and Australian researchers, especially early and mid-career researchers. And there's research activities relevant to Pacific Island studies, including those in French overseas territories. And it also supports research activities with the potential to support the development of strategic alliance between France and Australia. And the last program on the specific area of science is the Antarctic Research Grant. It's quite new because it hasn't been yet launched. And this research funding program aims at supporting collaboration between France and Australia in all fields of science related to Antarctica and the Southern Ocean. Funding through this program is designed to facilitate research exchange between Australia and France and to support research and field work. Yeah, so thank you very much for your time. And if you have any questions, feel free to ask me.
Merci Nathalie. Parfaite présentation.
Thank you very much, Nathalie, for this perfect presentation. And that is a very fit conclusion to this webinar, because the objective of that webinar is really to promote collaboration. So it's great to see that there is funding for such collaboration. So thank you very much for this. Any questions? No, I can't see any. Well, you have the contact details of all speakers, so you can get in touch. We're on time, so let's keep it that way. Many thanks to our speakers, many thanks to our partners that you can see named on this slide. They're the ones who made it possible, and many thanks to the interpreters who are doing a great job. Well, thank you very much, sir. It's our pleasure.